Clone graph. If you want to ace technical interviews at FONG and beyond, clone graph is a classic you must master. This pattern mastery 100 essential tests whether you truly understand recursion, graph traversal, and deep copying data structures. Did you know that a significant portion of candidates lose points here by shallow copying nodes, missing cycles, or failing to preserve graph structure? By getting this one right, you'll stand out in any interview and be ready for a whole family of graph problems. Here's the breakdown. You're given a node from a connected undirected graph, where each node contains a value and a list of neighbors. Your job? Return a deep clone of the graph, a new set of nodes, with the same structure and connections as the original, but no shared nodes. You can't just return the same nodes or rewire incorrectly. Cycles and shared neighbors make this tricky, so you need to carefully manage which nodes you've already cloned. Let's assess the challenges. Graphs can have cycles, so a naive recursive or iterative copy may loop forever. Nodes might be shared among neighbors. If you clone each node multiple times, the structure gets corrupted. We need a way to remember which nodes we've already cloned, so we can reuse the correct references. Use a hash map, dictionary, to track each original node and its corresponding clone. Traverse the graph, BFS or DFS. For each node, if it hasn't been cloned, make a new node and put it in the map. Then, recursively/iteratively clone all its neighbors. Here's our plan. Edge case. If the input node is none, return none. Create a map, old to new equals, to track original to clone nodes. Define a helper, DFS or BFS. If a node is already in the map, return its clone. Otherwise, clone the node, add it to the map, and recursively clone all neighbors. Return the clone for the input node. This is solution 1. DFS recursion. Time complexity, O(n plus m). We start by defining a class named solution, which simply organizes our method. This defines our function clone graph, which takes a starting graph node and returns a deep copy of the entire graph. We check whether the input node is none. If there's no graph to clone, there's nothing to do. So in the case of an empty graph, we simply return none. We create a dictionary called cloned. It will map original node clone node. This ensures we never clone the same node twice and also prevents infinite loops in cyclic graphs. We define our helper function DFS, which performs a depth-first search to clone nodes one by one. If we've already created a clone of the current node, we return it immediately. This avoids duplicate nodes and handles cycles safely. So if the node has already been cloned, we just return the saved copy. If the node has not been cloned yet, we create a new node with the same value as the original. Right now it has no neighbors. Those will be added next. We store this new clone in our dictionary so we can reuse it later. We loop through all the neighbors of the current node. Each neighbor is another connected node in the graph. For each neighbor, we recursively clone it using DFS_NA and then append that clone neighbor to the new node's neighbor list. This is how we rebuild the structure of the graph. After cloning the node and all of its neighbors, we return the completed clone. Finally, we start the DFS cloning process at the input node and return the fully cloned graph. Final wrap-up. And that's how this algorithm works. It first creates a mapping to track clone nodes, then uses DFS recursion to clone each node and its neighbors exactly once, gracefully handling cycles and shared references. Efficient, simple, and elegant. Test case check. Clone graph using DFS. Let's test our function using this input. 2, 4, 1, 3. 2, 4, 1, 3. These lists represent the neighbors of each node in the graph. For example, node 1 connects to nodes 2 and 4, node 2 connects to nodes 1 and 3, and so on. Here's why the solution works. We perform a DFS traversal of the graph. Whenever we encounter a node, we create a copy of it and store the mapping in a dictionary. Then we recursively clone each of its neighbors. If we revisit a node we've already cloned, we simply return the existing copy, preventing infinite loops in cyclic graphs. And that's exactly what our program outputs. 2, 4, 1, 3. 2, 4, 1, 3. It perfectly matches the expected clone structure, confirming that the graph has been duplicated accurately. Wrap up. So, our implementation is correct. The algorithm successfully creates a full deep copy of the graph using DFS and a hash map, efficient, accurate, and reliable. Solution 2. BFS iterative. Time complexity, O(n plus m). We import dec, a fast double-ended queue that lets us pop from the front efficiently, perfect for BFS. We define a class called solution to store our cloning method. This defines our function clone graph, which returns a deep copy of the graph using BFS instead of recursion. We check if the input node is none. If the graph is empty, there's nothing to clone. So we return none in that case. We create a dictionary cloned, starting with a clone of the input node itself. This maps original node clone node and ensures we never clone a node twice. We create a BFS queue and begin with the starting node. This queue will help us explore the graph level by level. We begin our BFS loop. This will run until we've processed all nodes reachable from the start node. The BFS traversal touches every node, n, and every edge, m, giving us on plus m, time. We take a node from the front of the queue. This is the node we're currently cloning neighbors for. We loop through each neighbor of the current node. Every edge in the graph gets checked exactly once. If the neighbor hasn't been cloned yet, we need to create its copy now. We create a clone for the neighbor and store it in our dictionary. Since this neighbor hasn't been processed before, we add it to the BFS queue so its neighbors can be cloned later. Regardless of whether the neighbor was newly cloned or already known, we connect the cloned current node to the cloned neighbor. This recreates the correct graph structure. Finally, we return the cloned version of the starting node, which is now the head of a fully copied graph. Final wrap-up. And that's how this algorithm works. It first creates a queue and a mapping of original nodes to clones, then performs BFS to clone each node and link all neighbors, ensuring the entire graph is rebuilt iteratively. Efficient, simple, and elegant. Test case check. Clone graph using BFS. Let's test our function using this input. This represents a graph with just one node, and that node has no neighbors. In other words, it's a single isolated node with an empty adjacency list. Here's why the solution works. We start by cloning the initial node and placing it in a BFS queue. Then we process the queue level by level. For each node, we look at all its neighbors. If a neighbor hasn't been cloned yet, we create it and push it into the queue. Then we connect the cloned node to its cloned neighbors. And that's exactly what our program outputs. This confirms that the BFS cloning logic works correctly even for the smallest possible graph. Wrap up. So, our implementation is correct. The algorithm successfully clones the graph, even in minimal cases, using a clean BFS traversal and a mapping of original to cloned nodes. Efficient, accurate, and reliable. Clone graph. Let's do a recap. So, we just tackled one of the trickiest graph problems in interviews, clone graph. It's a true test of your understanding of recursion, traversal, and deep copying complex structures. Once you master this, you'll be ready for an entire class of graph and network-related problems that interviewers love to ask. Breakdown recap. At its core, this problem asks us to create a deep copy of a connected graph, meaning we build entirely new nodes that mirror the original connections perfectly. The catch? Graphs can contain cycles, so careless recursion can loop forever or duplicate nodes. Assess recap. We compared possible approaches. Brute force copying fails because of repeated nodes, while using recursion with memory tracking works beautifully. The key insight was to use a hash map to store already cloned nodes, so every original node maps to exactly one copy. This ensures no duplication and handles cycles cleanly. Structure recap. Our plan was simple yet powerful. Handle the base case when the graph is empty. Use DFS to explore and clone each node. Store each clone in the map, then recursively connect its neighbors. That's it. A clean, recursive structure that mirrors the graph one layer at a time. Implement recap. We implemented the DFS-based solution, ran it through LeetCode, and it executed flawlessly. No infinite loops, no shallow copies, and no structural mismatches. The cloned graph preserved every connection while remaining fully independent of the original. Check recap. After running multiple test cases, the cloned adjacency lists matched perfectly. All cycles, neighbor relationships, and node values aligned as expected. All test cases passed with optimal performance. Closing insight. The big takeaway? Clone graph is all about thinking recursively, breaking complex structures into smaller, familiar problems. Once you grasp how to track references and prevent duplication, you unlock the mindset needed for tackling any advanced graph or tree problem in technical interviews.